welcome to my channel. I'm in Coaching Center. So today I'm going to explain your 12th standard chemistry first chapter, that is solid state. So as you know, solid are the chemical substance which are characterized by defined shape and volume. So there are types of solid. There are two types, that are crystalline solid and amorphous solid. So let us see the difference. They may ask this for 2 to 3 marks in your final exam. So difference in the between the crystalline solid and amorphous solid is these have definite and regular arrangement of the constituent particles in space. In space they have different arrangement, but these do not have. The amorphous solid does not have definite arrangement, and crystalline solid they are true solid, but the amorphous solid they are super cold liquid, or they are little bit solid. And the crystalline solid they have long order arrangement of the particle. They have long arrangement of the particle, but in the amphoteric solid they have short order arrangement of particle. They are arranged the particles in very short, and these are anisotropic in nature. These are the crystalline solid are anisotropic in nature, and they are amorphous solid. They are the isotropic in nature, and they have a sharp melting point. The crystalline solid and amorphous solid they are melt over a certain range. They melt under a certain range of temperature. Crystalline solid they undergo a clean cleavage when cut. When cut they go a clean cleavage. When they cut they go clean cutting. But in the amorphous solid, if we cut, it goes irregular. It will be the cutting will be not correct. So this difference they may ask in our final exam. Next is types of crystalline solid. So let us know types of crystalline solid. They are constituent particles. The character constituent particles, and they are ionic solid. They are positive and negative ions. Covalent bond atoms, molecular solid molecules, and melting metallic solid positive ions and free electrons they have. And next is bonding force, electrostatic attraction or covalent. It will be covalent, solid is covalent, and molecular solid is van der Waals dipole, and melting solid or electrostatic. Next is hands off, hard or soft. So hard and brittle ionic bond, and the covalent bond are very hard, and molecular solids are very soft, and metallic solids are hard and soft, both always. Next is conductant, conductor in a ionic bond conductor in a aqueous solution, and covalent bond very hard non-conductor. Molecular solid very soft insulator conductor, and metallic solid hard and soft good conductor they are. Next, structure of determination by X-ray diffraction. So when a beam of X-ray falls on a crystalline plane composed of regular arranged atoms or ions, the X-ray are diffracted, and if the waves are in phase after refraction, there will be difference in distance travelled by two rays. There will be difference. Hence, there must be equal to an integral number of wavelength there may be, and n by lambda for constructive. So the path difference is equal to wy plus yz here, wy plus yz. So xy sin theta plus x small xy sin theta. So 2xy sin theta is equal to 2d sin theta. So n lambda is equal to 2d sin theta. This is the equation called Bragg's equation. So this equation is called as Bragg's equation. So which equation is called as Bragg's equation means n pi is equal to 2d sin theta is called as Bragg's equation. And here lambda is wavelength of X-ray, d is the distance between the atomic planes, and theta is angle at which interference occurs. Next is unit cell. So the smallest geometric portion of crystal lattice, which can be used as a repetitive unit to build up the whole crystal, that may used as repetitive unit to build up the whole crystal, is called as unit cell. And there are types of unit cell. The first is simple or primitive unit cell, in which the particles are present at the corners only. So they are present at the corner only. And face-centered unit cell, in which the particles are present in the corner and they are also present in the center, are called as the face-centered unit cell. Next is body-centered unit cell, in which the particles are present at the corner as well as the center. At the just only in the center it is present. Here these are the present at the corners. Face-centered unit cell, they are present at the corners and at the center of the two optic faces, the center of that. And unit cell, simple face, body, end. They have corners 8 into 1 by 8, face 0 0 and total is 1. And face center, they have corners 8 into 1 by 8, face 6 into 1 by 12, so therefore it has total 4. Body center, it has 8 into 1 by 8 and center 1, so therefore it is 2. And end centered, they have 8 into 1 by 8 into 2 into 2, so therefore they have 2 is the 2 total numbers. Next is 7 crystal system. There are about 230 crystal forms which have been grouped in 14 types. They are grouped in 14 types and they are called as Bravis lattice on the basis of their symmetry and 7 different crystal systems. So 7 crystal systems, they are crystal systems: cubic, tetragonal, rhomboid, rhombohedral, rhombohedral, orthobic, and monoclinic, and triclinic, and hexagonal. So it has A is equal to B is equal to C, and tetragonal has A is equal to B not equal to C, and third one has A is equal to B is equal to C. Fourth has A is not equal to B, not equal B not equal to C, A not equal to B, B not equal to C, and A is not equal to B, B is not equal to C, and A is equal to B but B is not equal to C. These are the equation. Next is packing fraction. So it is defined as the ratio of the volume of the unit cell that is occupied by the surface sphere to the volume of the unit cell and by the unit cell, and they are primitive cubic unit cell. Atoms touch each other along edges. This is called as primitive. Face centered. Atoms touch each other along the facial diagonals. Diagonals it touch it. And body centered unit cubic cell. Cells atoms touch each other along the body diagonals. Not face diagonals, body diagonals if they touch, then it is called as. So coordination number, if it is defined as the number of particles immediately adjacent to the each particle in the crystal lattice. Next is close packing in the crystal. Two-dimensional packing of constituent particle. Square closed packing, space occupied by sphere is 52.4% here. So like this you have to write, and here Cn is 4. And hexagonal closed packings, they have 60.4, hence you have to, it is more efficient. So this is more efficient. So okay friends, clear explains. I will explain the other topics in the next video. So okay friends, like to comment and subscribe my channel, coaching for more video. I will see you in the next video. Till then, take care. Have a nice day. Bye.